Okay, hello everyone. Welcome to this video, Power System Protections. The topic today is very short, a very generic and brief introduction about overcurrent protections, okay? Again, before we start, I would like to say thank you to everyone that has been following my videos, especially the Power System Protection community. I would like to remind you that the slides, they are available at my ResearchGate page, and also some of the practical examples, numerical examples, scripts, and so on, they are located at my GitHub, okay? If you are watching this video, I imagine that you are following my YouTube video, but also please feel free to add me at Twitter or LinkedIn, okay? Well, but let's go back to this class, okay? As I said before, today the class is a very, very short introduction about overcurrent protection, okay? Why do I say those adjectives very short, very brief, because I know in the power protection community, power system protection community, overcurrent is a very, very broad and very, very complex topic, okay? Later, I will discuss some of the devices using for protection, the fuse, the recloser, the sectionalizer, and so on. And I believe people from the power system protection side, they will agree with me that you can spend weeks or even months or even years just working with one of those devices. I mean, just coordination and protection using fuses, that is a very interesting topic, okay? Today, I only have a few hours to make a generic introduction about overcurrent protection. In these slides, you will find is the classical non-pylon overcurrent protection for transmission system, or the classical overcurrent protection for distribution feeders, okay? What is the plan for today? Okay, the plan is, I would like to start with a short introduction about overcurrent protections. Then I will go across some of the most popular protections device used for overcurrent protection functionality. The classical one, probably the oldest one, the fuse. Then I will have a short discussion about reclosers, then sectionalizers, and I will move to the overcurrent relay. Especially, I will talk about the instantaneous overcurrent relay, the definite time overcurrent relay. Then I will go to the inverse time relay to close with the standard inverse definite minimum time, okay? There are 3 examples in that section, and then I will start with the discussion about basic principles of grading. I mean, when we are interested on identify short circuit overcurrent fault, there are at least 3 techniques that we use for grading: discrimination by time, discrimination by current, and the third one is the combination of time and current at the same time, okay? I will just present what is coordination procedure for overcurrent functionality. However, you will realize that is a very broad and very complex topic, okay? Finally, I will focus on application of definite time overcurrent relays for protection of distribution feeders, and then an application for the inverse definite minimum relay time relay, okay? Again, for distribution feeders. Then a numeric example number 4, summary, And there is a homework, if you are following my classes, a homework that you can do at home, and later you can compare your results, okay, with the provided results. Okay, what to say about overcurrent protections? Well, I think the overcurrent protection is probably the oldest protection system that electrical engineers install at power systems, okay? I think when we start to create the power system, probably 100 years ago, we start to put small generation systems and some loads together, and at the very beginning, the first problem was the first problem that happened, or probably one of the first that happened, it was the short circuit. And those short circuit create very high currents. Typically, the short circuit create high currents, and the power engineer at the time must take action in order to avoid destroying the devices or putting on hazard the people. As a consequence, probably the first automatic protection, probably the first equipment responsive to the excess of currents, it was the fuse, okay? Of course, it was a solution for the difficulties that at that time happened, and then when the power system started to be more mesh and bigger, higher short circuit currents and so on, well, power system protections engineer require the use of something more complex, okay, in order to provide selectivity to the electrical power system. And that is when create discrimination and grading between fuses start to be a big problem, and the rise of the the merge of or the rise of the overcurrent protection relays start to appear, okay? Today I can say that probably overcurrent protection is the most used protection scheme that you will find inside a power system, especially if you are at distribution level or inside an industrial plant, okay? Fuses, they still in the power system, especially to medium low voltage distribution downstairs inside the industry and even inside your houses. Many reasons. One of them is that the fuses, they are extremely cheap, very simple, and they are a direct acting mechanism, and to be honest, for some application is probably the best solution, okay? Well, now time to go for the class. The protection against the overcurrents, it was probably the first one that appeared inside the power systems, and it was simple at that time because you can say, okay, if the current is above a number, you will say that is a fault condition, and it was simple to identify and to discriminate the fault condition. However, something that you must understand is that the overcurrent protection should not be confused with the overload protection. The overload protection is typically the one that we use for a low voltage system, and is related mainly with the thermal capability of the device, okay? What I am trying to do, what I'm trying to say is that overcurrent protection that I will be discussing here is mainly the overcurrent that is extremely high, and it's related with the classical short circuits, okay? Of course, overcurrent protections, what we want is to stop the overcurrent moving inside the power system, okay? As I say before, probably the fuses, they are the oldest technology, one of the oldest technologies, and the fuses are extremely simple in the mechanism and the way that they are working. However, However, they are another kind of devices. For instance, in low voltage, you can find those small blocks that we call direct acting trip mechanism inside the circuit breaker. Okay. And of course, when you start to move to higher voltages, the functionality of overcurrent protection must go outside the circuit breaker. What I'm trying to say is those molded case circuit breaker that you can find inside your home, they are direct acting trip mechanism, and they are included inside the circuit breaker. However, when you move to high voltages, the functionality of the overcurrent discrimination must be outside the circuit breaker, and that is the place where relays start to be very, very important. Okay. At transmission level, we need to be sure that the power system can be planning and designed in an extremely careful way in order to minimize the probability of faults. However, the power system is subject of faults, okay, especially at transmission line, because they are the longest component inside the power system, and it's typical that because they move in different geographical areas and exposed to many things, a short circuit can happen. Okay, for that reason, what I want to say is that the short circuit is probably the most important source of cause for damage at the power system equipments. Okay. We need to be clear that there are many kind of faults. Some of them related with the loads. Some of them they have they are affecting not only the magnitude of the current, also the directionality of this current, especially in mesh system like the transmission lines. Okay, for that reason, as you can see, the transmission line protection using overcurrent is a bit more complex problem, especially because the directionality of the currents. Okay. Something that is very important is that for transmission system, the length of the transmission lines, they have a special effect, okay? Because they define the total impedance that is involved inside the short circuit. I mean, limiting the short circuit from the sending terminal to the short circuit point. I will discuss a bit more about this later, okay? What I would like to say is that typically relays are used as primary protection for transmission lines, especially for the primary segment that you are inside the transmission line. However, those relays can be used for backup protection, okay? One interesting thing is overcurrent relays, they are useful. However, one of the problems of using overcurrent protections at transmission level is that using only the magnitude, the current magnitude, is not good enough for transmission system. Transmission systems are typically mesh, there are multiple infits, and there are many possibilities that you have the same current magnitude for faults and non-fault conditions. And that is the reason that using overcurrent protection alone is not a quite typical practice at the transmission level. Some of my colleagues from the utilities, I know that they will complain to me and they will say for transmission systems we use is mainly distance protection. Yes, I totally agree with you, but in this case I am trying to explain to the young minds that there is a possibility that you can use overcurrent protections at transmission level. However, you must know the complexity and the problems involved of that, okay? I will not go against 40 years of field experience. I'm just trying to say that the brilliant young minds must understand what is happening in the field, okay? Okay. Now going to the overcurrent protection. Typically, the overcurrent protection depend on the magnitude. Okay, you must remember that we use the ANSI standard to define some codes that identify the protection functionalities, and typically for overcurrent protection, the non-directional overcurrent protection is basically the ANSI 50, that is the instantaneous overcurrent, and the ANSI 51, that is the time overcurrent. Okay, the good news about the instantaneous overcurrent is non-directional instantaneous overcurrent is that it's extremely simple. This protection is only reacting based on the magnitude of the current. However, there is a problem if you have the fault in F1 or F2, because the relay is not able to identify if the fault is inside the transmission line or is on the other side at the bus number 1. For that reason, there is another overcurrent protection, the ANSI 67, that is the directional overcurrent relay. The directional overcurrent relay, this relay is monitoring the magnitude, of course, the current magnitude, and can identify faults at F1, but also because it's also having a sample from the voltage, the bus voltage, this device is able to identify the location, the directionality for the current, and it's easy to identify if the fault is happening at the transmission line side or if the fault is happening at the bus bar side of the circuit breaker. Okay, now I need to be clear. Transmission line protections and distribution line protections, they are very, very different, okay? And of course, the difference is because many things related with power systems characteristic. Distribution system, they are a higher resistance comparable with the reactance. The topology is mainly radial topology. As a consequence, distribution line protections or feeders is it's very, very simple to use the short circuit current to discriminate short circuit locations. Okay, typically, okay, again, probably some of my colleagues from the utilities, they will complain depending if you are using overhead feeders, transmission lines or distribution lines, or using underground cables, the short circuit levels can be a big problem. Okay, transmission system, the main difference is that we have mesh, multiple infeeds. As a consequence, the directionality of the short circuit current start to be a problem. Okay, in distribution system, we have several devices that we can use for protection. The classic one, the fuse, the sectionalizer and reclosers, instantaneous overcurrent, typically installed at the distribution substation, and also inverse time delay and overcurrent relays installed at the substation. Okay. On the other side of the equation, we have transmission line protection. Overcurrent is not typically the unique function used for transmission lines. However, that is a possibility. Fuses, they are not typically used in extra high voltages. However, that is a possibility. Sectionalizers, they are not quite frequently used at transmission system, but that can happen in some cases. Reclosers, yes, there is a possibility that the reclose function is enabled into the power circuit breaker. Okay, reclosers as device in extra high voltage is not typical. However, what we do is typically enable a functionality to the power circuit breaker that allow reclose. Okay, instantaneous overcurrent relay and some other functionalities. Directional overcurrent is quite typical use at transmission system, and also distance protection and pilot protections, they are quite typical at the transmission side. Okay. from now on, I will focus mainly on topologies like I am presenting over here. Here we have an equivalent big system. There is a transmission line. There are two bus bars, number 1 and number 2. Okay. Its line represents the equivalent impedance of the transmission system. It's a series reactance over here. What is the interesting thing? Well, I don't know if you realize, but it's important that we identify if we are working with a short line or a long line. If we are using a short line, that means that the impedance of this line is extremely small compared with the equivalent system. The current, the short circuit current, three-phase short circuit current, and the point 2, it will be smaller. It will be smaller than the short circuit current at the bus bar number 1. However, it will be not so big depending of this number over here. However, what's happened if we have a very long transmission line? Well, if we have a very long transmission line, the inductive reactance is higher. It could be several times the equivalent reactance, and as a consequence, the fault levels at the bus bar number 2, they will be significantly smaller compared with the short circuit at the terminals of the equivalent system. And that at that moment we will say that is a long line. Okay. What I want that you understand is that depending on the reactance, inductive reactance of this line, series line, you can have cases where the short circuit difference between two bus bar it's extremely big, or the difference is very small. Okay. Now let me talk about one of the most used overcurrent protections used, especially for medium voltage and low voltage, and that is the fuse. The fuse is probably one of the oldest devices used for overcurrent protection. What is the reason for that? Well, it's extremely simple, and that's make this reliable and cheap. And that is extremely simple. The point here is that the fuse, as you can see here, the fuse, inside the fuse there is a small conductor. And that small conductor have a very specific properties. And if the current goes above a specific limit, the heating at that very specific conductor will reach the melting point. And at that moment, when the conductor melts, you are stopping the current. That is brilliant. There is a reason that I say to my students, power system has been smart for a century, because electrical engineers working at the very early stages of power system, power utilities, they were extremely clever. They used basic physics, very basic physics, in order to make the power system work. Okay, and the fuse is one of the technological examples. Something extremely simple, a conductor that fuses when the current is above a limit. And that is extremely clever and just basic physics. You don't need internet, you don't need ICT. If you look over here, this is what we call the fuse link. The fuse link is must be installed together with what we call the fuse holder. Okay. Typically for low voltage and relative high currents, we can have this kind of fuse holder. Okay. For even bigger, the complication about the fuse holder start to be a problem. Okay. For distribution level, the way that those fuse holders are designed is basically considering the voltage level. Okay. Well, here you can see a cross-section that this is extremely lovely. Here you can see the cross-section of one of these fuses. Okay, You have here two terminals. You have two terminals. Inside you have the conductor that I was talking about that was extremely clever design. And inside, that is what we call the fuse element. And inside the fuse element, there is a very small breaking point. And the operation is extremely simple. When the current starts to increase here, you are dissipating heat. But if the current moving through the fuse is extremely high, the fuse will melt this small piece of metal and then you will stop the current circulation. Of course, you need a space, a confined space, in order to stop the arc. And we use silica sand typically for medium and low voltage fuses. And here in this area is where the energy related with the arc is dissipated, okay? On the right hand side of this slide, you can see a generic time current characteristic. You have here some current. If the current is equal to this, the fuse can keep working, but immediately after the current is when the current moving across the fuse is above this number, well, you will start to have very fast and faster and faster and faster and faster operation, okay? I will show you a couple of more specific time current characteristic in fuse lines, okay? However, what I want to show you is this very important plot over here, okay? On the left-hand side, you can see the current. Here, in this dot line, you can see the short circuit current. You can imagine the current is going to reach this maximum peak over here. However, when the current is moving across the fuse, we have some time that the fuse start to be that the fuse is a bit increase the temperature of the conductor. That is what we call the pre-arcing time, okay? This is the moment that we are dissipating energy. We are dissipating energy, but it's only because the heat up of the conductor inside the fuse. The situation starts to be very interesting is when we reach a current that the heat that is inside the conductor, inside the fuse, is enough that the melting process starts, okay? At this moment, we call that the cutoff current. For instance, in this application, we are talking about 5 kiloamps. At 5 kiloamps, we have the melting process, and of course, because the fuse tried to open, or to be honest, start to open, there is a voltage that appears across the terminal of the fuse. Because when the fuse is working, there is a very small voltage across the fuse. There are almost zero losses. When the fuse start to heat, we start to have more voltage because the resistance start to increase to dissipate more heat. And then we have the cutoff current, and that is where the melting process starts, okay? When the energy coming from the arc start to be dissipated inside the sand. At that moment, we can say that we are inside the arcing time. The arcing time is the time that we have the arc inside the fuse from the very beginning until the current disappears, okay? The interesting thing here is we have a huge increase on the voltage because that is the voltage across the terminals of the fuse created by a very high current moving in a very high resistance, and that is the recovery period. Then we have a massive dissipation of energy, and then everything continue, okay? You can read more about this. You can read more about this in several books, including Packel or including another book about protections. Okay, it's not my idea here. Explain the full the full details of the physical phenomenon. There are many books dedicated only for fuses, okay? Coming back to fuses, they have a lot of applications when you are working at low voltage, especially residential installations and industrial plants, okay? Typically, we can identify different type of fuses. The fuse that I was talking about a few minutes ago is what we call the non-current limiting fuse, but there are some other fuses that they have a very specific characteristic, okay? As I said before, here the voltage start to increase because during the pre-arcing moment, the resistance start to increase, okay? But there is a moment when the arc is start that the resistance it will increase so fast that try to send the current down to zero, okay? In this case, the resistance that is stopping the current increase but is not controlled. When I say that is not controlled, that is the case of non-current limiting fuses. However, there are some fuses that you can have some control about the resistance that is created during the arcing period, okay? And that is the use of current limiting fuses. Current limiting fuses, they have a very interesting characteristic. When the fuse element is melting, the current start to introduce a big resistance, but it's a controlled resistance based in physics that try to keep the magnitude and duration of the interruption control in a formal way. Here again we have the pre-arcing time, and this is the pre-arcing time, and then you have here the arcing time. What is the main difference between this curve and the curve that I presented before? I believe here you can see a suddenly drop, a very fast drop on the current, but here is quite smooth, and to be honest, it's almost linear or something similar to that. And it's mainly because this limiting range that the fuse have the possibility to introduce this resistance, limiting the current, the current that is moving across the terminals, okay? Here I want to show you, you must be careful between current limiting fuses and any other non-current limiting fuses, okay? Here you have the time current plot for a limiting fuse, and here you have for one expulsion fuse. Something that you must realize, this characteristic is almost more linear compared with this one. And in both cases, you must understand that they are typically two curves defined for a fuse. In a fuse, there are many curves. However, I will talk about the two most, the basic ones, okay? I know that people from protections, they can complain because they are more explanation that you can do, but again, I will go very simple for my students. They must understand this curve here define the starting point of melting the fuse element, okay? And then here we have here the total clearing, and the total clearing is defined by the current and the moment that the fuse stop the current circulation, okay? What is the idea of this? Well, for overcurrent coordination, you need to be sure that the fuse is acting at the proper time. And if you have two fuses, one behind the other, what you need to do is create a separation between those curves, okay? In the next slide, I will discuss a bit more about selectivity, okay? In distribution system, you have the cases of several fuses in the same coordination line. For instance, here we have a transformer, a distribution transformer going to the main substation. Here you have a feeder. Let's say this is a feeder, and we have this fuse here upstream, and downstream we have here another fuse. Okay. If we assume that there is a fault, a short circuit fault here at the point F, the fuse that must work is the fuse located at the position here. It's the only fuse that must work. This one doesn't not open, this one does not open, this one does not open. If any of these in the coordination line opens, that means we are in troubles because we lose selectivity. For a moment, I will focus here in those two fuses, okay? Let me call the upstream fuse A, let me call the downstream fuse B, and here we have the fault, okay? The fault F. We can call this fuse the fuse on the line side, and we can call this one the load side, okay? What you have here on the right hand side is the plot for the short circuit current in blue color, and this is the characteristic that is happening at fuse B and on the top for fuse A, okay? What we want is keep selectivity. For that reason, this fuse F, the fuse B, must open during the short circuit current at the point F. For that reason, we need to say that the clearing time of this fuse must be smaller compared with the clearing time of the fuse A, okay? Again, let me explain. What we want is that this fuse open first and then this one. To do so, we define there is a clearing time here that is a characteristic of this fuse. This is the time, but the clearing time of the fuse upstream must be bigger in order to allow this fuse B to open first. But we need to be careful, okay? Because when the fault happened here at F, the short circuit current is moving in this branch, it's a series branch, and as consequence, that short circuit current is moving in both of them. And when this fuse see the currents, this one also sees the current, but the energy that is dissipated here should be equal or less than the melting energy on the fuse A, okay? Overcurrent coordination for fuses is something that is extremely simple if we define time difference between positions on the fuses, okay? Okay, now let me go to another interesting device, and that is the recloser. The recloser is typically used in medium to low voltage distribution side. It's typically a device that have automation and is able to detect phase and phase to ground over current conditions. And this device has the possibility to open currents. I mean, this device is open to interrupt circuit currents over currents. And the idea is that this device is coming with some controller that is able to open the circuit breaker and have a counter, and this counter can be used to take actions like opening again the circuit breaker if there is any kind of short circuit. Okay, here you can see the cross section of one of those reclosers. Is typically a couple of bushings. You can see the bushings, terminals here, and you have something similar to a circuit breaker and an action mechanism, okay? And inside this box you will find the controller, okay? Okay, the recloser is quite useful at distribution level for a very interesting and simple reason, okay? At distribution level, primary distribution level, especially if you are using overhead distribution lines, it's typical that the short circuits, they are just temporary short circuits. I mean, a tree goes near to a distribution line, then the isolation is disrupted, there is a small short circuit, but the idea of the recloser is when the recloser see the overcurrent, they open and they wait for a few seconds or cycles, depending on the manufacturer, but then the device will close again. What is the idea of reclosing? The idea of reclosing is that you have a fault that is a temporary fault, and reclosing, probably the source of this short circuit will disappear, and then when you reclose, you energize again the system and you recover supply to the customer. That is the reason that we use a lot, in some countries we use a lot this recloser for distribution system, okay? Now let me talk about, I will not go in full details here, but let me talk about the auto-reclosing timeline, okay? We call auto-reclosing timeline the sequence that represent the operation of the reclosing device, okay? Here we can find the ANSI 79. 79 is the auto-reclosing, okay? We say auto-recloser because this is an automatic recloser, okay? In this case, the timeline, what is showing here on the horizontal axis is time. And you can see in this case, there are two auto-reclosing time, following by a reset. Here you can see the first auto-reclosing attempt, the second auto-reclosing attempt, and then there is what we call the reset of the reclosing, okay? In this example, we assume that the first auto-reclose, the breaker was not successful, I mean, the interruption of the fault was not successful, and the fault detection device retrieved again the breaker, okay? Initially, the auto-reclosing delay settings is 0.2 seconds in this case, and then since the closure of the breaker, this is basically using an auxiliary contact that is coming from the breaker and indicate if the breaker is open and closed. The second auto-reclosing delay is provided typically is what we call a long reclose. In this case, the setting for this slow reclose is 15 seconds, and then there is a reset interval that it's starting at every time that the breaker closes. In this case, the reset timing function is halted or is stopped and reinitiate when the circuit breaker trip. Okay, the auto-reclosing relay will reset to the initial state only if the breaker doesn't open during the reset interval. What I'm trying to say is if the circuit breaker doesn't open here, then the auto-recloser will reset and will go back to the original position, and if anything happen again, the same history with the first short reclosing, the second slow reclosing, and then with the reset delay will happen again. Okay, let's keep rolling. And now what I want to show you is here we have we have a power source, we have a transmission, a distribution transformer, there is a circuit breaker, there is a recloser, there is a fuse, okay? Here in this time current plot, we have in blue color the plot for the fuse that is located here. We have the minimum melting and the total melting curve here. Then we have the curve related with the recloser. We have a slow curve for the recloser. We have, the slow curve for the recloser, the fast curve for the recloser. And then we have a slow curve coming from the breaker here and the fast curve of the breaker over there, okay? Well, to be honest, here in this, on the left-hand side, what we have is the time current plots of every single device. We have 3 devices. They are 6 curves over there. On the right-hand side, you can see is the coordination, okay? How do we get coordination here? Well, very simple. If we have fault at F, the first device that must work is the fuse. Then, if this fuse is not opening or something happened, we put here the curve for the recloser, and that is the slow curve for the recloser. And then the third line is we are using the setting for the slow curve for the relay overcurrent relay at the circuit breaker, okay? Now I will show you a device that is the sectionalizer. The sectionalizer is it's mainly a switch. It's not a circuit breaker, okay? You must be careful. A switch is not able to interrupt fault currents, okay? However, this sectionalizer is coming with a control unit similar to the recloser, okay? Sectionalizers, they are used together, working together with the reclosers, okay? Or they can work together with a classical circuit breaker with a overcurrent relay, okay? What is the idea? The idea is that this device is taking in account the times, number of times that the circuit breaker open and take decisions to open the feeder if the fault is detected when the circuit breaker closes again. Okay, I will show you here. Here you have a recloser. Here you have sectionalizer 1, 2, and 3. Okay, I will care is just about the recloser. Here we have the timeline of action of this recloser. Red color means close, green color means open, okay? And here we have the sectionalizer, in this case is S1. Again, red is on or closed, and green is open, okay? Now what you need to understand is the following. What is the idea here? Well, initially the recloser is closed, the sectionalizer is closed, and also the circuit breaker is closed, but there is a fault at F. When we have the fault, the circuit breaker will open, okay? In this case, the sectionalizer is open, the circuit breaker open, there is a time delay here, 0.5 seconds. Then the recloser will say, okay, let me try again and see if there is a fault. The circuit breaker close, again the overcurrent mechanism here say there is a fault at F. As a consequence, the recloser will open for second time, and because this is a slow reclose action, it will wait 10 seconds. But in this case, as you must remember, when the fault happened, this sectionalizer saw the first open, and then saw the try to close, and the fault current is still moving across the sectionalizer. For that reason, this sectionalizer realized, oh, the fault is inside the feeder that I am protecting, And as a consequence, after a short delay, the sectionalizer will open this feeder. Okay. However, you must notice something. In this area, in the deadline 2, you can see that the circuit breaker opened. As a consequence, there is no load current, there is no fault current, there is not any current moving inside this circuit. This sectionalizer can open because there is no current moving over there. They open the contacts, the sectionalizer open and stay open, and then the recloser will close again the contacts, and we keep providing services to the feeders at 2 and 3. That is the logic behind the sectionalizer when you are using sectionalizer in parallel connection, okay? Something similar is when we have sectionalizers in series connection. When you have sectionalizers in series connection, we have sectionalizer 2, sectionalizer 1, we have the recloser, there is a fault, the recloser open, and both reclosers start to take in account what's happened. The recloser open, then try to close, and that means, okay, because I saw the first and the second, I will say, okay, that means that the fault is downstairs. That means it's my responsibility as sectionalizer number 2 after a time delay open. Then the recloser will close the contacts, and we will keep feeding the load that is after the sectionalizer number 2, okay? To show you the logic and to show you that it's properly working is the following. Again, there is a fault, but now the fault is located between 2 sectionalizers. The reclose open, try to close using a faster reclose, there is a fault, and the reclose open, okay? When the reclose open, wait for the long delay, 10 seconds, then try to close again, and when the recloser close the contacts, again there is a fault. But the sectionalizer to see, okay, there is a third trip, and that means that the fault is above me. That means that the sectionalizer number 1 must take action. And as consequence, 1.05 seconds after the third trip, the sectionalizer 2, there is no current moving here because the main recloser, the main contacts are open. The sectionalizer number 1 will open, and then the recloser will close the contacts and will keep the service, okay? Okay, this was just a short introduction to show you how sectionalizers, they work together with the recloser, okay? However, settings of those sectionalizers, settings of those reclosers, they are not covered inside this short introduction about overcurrent protection, okay? What I will do now is I will move quite fast, taking or retaking again some ideas of the overcurrent relay, okay? You must remember we spent a full class talking about relays and the functionalities and the detection mechanism and also the way that they work, okay? Here I will go extremely fast because what we need to think about is that a typical overcurrent relay, they have a single input, and the single input is the AC current, okay? I am talking about non-directional overcurrent relays. The input is mainly the the AC current coming from the current transformers, the secondary winding of the current transformer, okay? And the output of the classical non-directional overcurrent relay is the tripping signal that is going to the coil for the circuit breaker and opening the circuit breaker, okay? The typical characteristic is very simple. The non-directional overcurrent relay, they care about the magnitude of the current. You can plot a circle, and that represents what we call the locus or the current diagram of the overcurrent relay. Okay, anything inside, that means that the current, the sensing current, is below the relay setting. There is no trip. That is what we call block. However, if the sensing current is outside the circle, we say, okay, that is a fault, please trip. Okay, that circle can be defined using the instantaneous setting. Okay, in a typical non-directional overcurrent relay, there are two typical functionalities. We can identify the time overcurrent and what we call the instantaneous and definite time action. Okay, in both cases, I mean, in the time overcurrent relays, the settings are typically the current dial settings or the pickup current, and for the time we define the time dial setting. Okay, the instantaneous relay, the only setting is the current dial, and that is what we call the pickup current. And the definite time, we can set up time and current. Okay, let me show you. Let me talk about the instantaneous overcurrent relay. Okay, instantaneous non-directional overcurrent relay is a very simple characteristic. If the current go above the pickup current, well, the relay will add in what we call the operating time, and that operating time is fixed and typically only few milliseconds. Okay, that is different to the definite time overcurrent relay. In the definite time overcurrent relay, we have controls on the time settings, and we have control on the current settings. We call this the pickup currents or current dial, and we call this the time dial. Okay, that is what I'm trying to explain here regarding the instantaneous. Instantaneous, there is not settings for the time. Okay, but in the definite time overcurrent relay, it's very simple. We have adjustment for currents and for time. Okay, now engineers realized that using this characteristic, it was not good enough to provide selectivity and coordination between overcurrent relays, and that is when we start to use what we call inverse time overcurrent relays. Inverse time overcurrent relays, they were created mainly to have a time current characteristic that allow flexibility in order to fulfill some requirements about severe short circuit levels and a very fast detection and cleaning. That is mainly the idea of the inverse time overcurrent relay. That if we have massive short circuit current, the relay will work extremely fast. But if the short circuit current is not so big, the relay will take some time, and that time will be defined by the inverse of the short circuit current. Okay, so more or less. I know that my colleagues from the protection environment, on the protection industry, they will say there are more explanations that we can do over here. Yes, but today we have only a few hours just to talk about this, and for my students, they only need to understand that that characteristic is defined to adapt the operation time based on some curve. Okay, The inverse time overcurrent relay was very, very useful for many years, and is still useful inside the power system because it was very simple to create them using the electromechanical relays, okay? And that is the reason that from the electromechanical relays is when the standardization starts to push a lot, and then we spread the use of those. With the era of static relays, well, right now you cannot imagine the different time characteristic that you can create. Okay, right now using the software, you can define virtually any time current characteristic that you wish. Okay, however, in this class, I don't have time to cover over there. There is a class about advanced overcurrent relays, and that will be a topic for talking about that. Okay. Okay, what we need to do is explain that those relays were created in order to add in a full defined characteristic between time and current that allowed that for big currents you have a small operating times, and for very small currents you have a bigger time. Okay, that was what allowed a better coordination between fuses and overcurrent relays, because fuses, they have a characteristic that they work extremely fast on the overcurrent, but that depends on the time duration of that overcurrent. Okay, for that reason, the instantaneous characteristic was not good enough to have a full coordination with the fuses, and that is the starting point for the use of the inverse characteristic. Okay. As I explained in the class about relay operation, the inverse characteristic follows something like the equation that I am pointing out over there, that the relationship between current and time is based in a constant. Okay. What I will do now is I will talk about what is the standard inverse definite minimum time. Okay, that is what we call IDMT. The IDMT is probably one of the most widely used time current characteristic. Okay, it has been defined, it has been included for many years. Okay, the mathematical equation that defines the relationship between currents and the operation time is here. Okay, what you need to understand is that overcurrent relay, non-directional overcurrent relay, they are mainly two settings. One setting that is related with time, and that is what we call the time multiplier setting. Okay. Some countries, they have another way to call this time delay, for instance. Another characteristic here in the denominator, you can coordinate what is the current that is moving inside the relay, and that is what we call the plot setting multiplier. In some countries, they call the current multiplier. Okay. What is interesting is that was the original idea of using the characteristic of current time that can be expressed by an equation. Okay. In America, in Europe, we have different standards. In America, we have the 637.112, and that is the standard that defines the inverse characteristic, okay, for overcurrent relay. And in Europe, we have the IC 60255, and that defines also the standard characteristic for this kind of inverse relationship between current and time. Okay, the IC 60255 define at least 4 different characteristics, what we call the standard inverse, the very inverse, the extremely inverse, and the definite time. Okay. On the other hand, the Americans, they have we have here the C37112, and we have the moderate inverse, the very inverse, and the extremely inverse curve. Okay, I would like to point out something. At the very beginning of the electromechanical relays, companies like Westinghouse and ABB and others, they start to create the relays by themselves. That was the time before the the time before the standardization, okay? And for that reason, some companies make famous the relays, and there are a couple of very interesting American relays that you can find, electromechanical relays, the CO8, that is an inverse relay, and the CO2, that is a short time inverse relay, okay? In the next slide, I will show you the difference. What is the difference of using a standard inverse, very inverse, extremely inverse, and so on. Okay, if we are using the IC 60255, the characteristic can be plotted in a time current plot, and what you can see is the following. All those curves, they have very different time current curve, but the idea of them is that some of them will work very, very slow, very, very slow for big currents, and then they will work extremely fast for high currents. But the difference between low currents and high currents, the operational time is big. However, if you look over here, the standard inverse curve, the difference on time, the time operation between low currents and big currents is very small, okay? What I'm trying to say is mainly the difference between a standard inverse, very inverse, extremely inverse, is it's not only the shape of this curve. The shape of that curve represents how fast or how slow will work the relay, but the different curve define the margin, the gap between low currents and high currents operational times. Okay. Okay, something similar happened here with the American standards. Okay. I believe on the right hand side you can see the plots. On the left hand side you can find the equations, and you can see the moderate inverse, the very inverse, and the extremely inverse, the IEEE ANSI plots for the standard overcurrent relay characteristic. And also we have included here the CO8 and the CO2 time inverse curve. Okay. Something that you must understand here is, again, the difference between those curves is, okay, what is the performance, the difference in performance between low currents and big currents? How big is the difference in operating time between low currents and big currents? And that is what defines the shape of this curve, okay? Why I am really interested on that you understand, and you can see here the equations, okay? The first thing that I need that you understand is that in Europe we use here the TMS, and the TMS is the time multiplier setting, okay? TMS represent the time multiplier setting, is equivalent to the time delay in the American standard, okay? It's mainly defining how to change the characteristic based on time delays, okay? The second thing that I need that you realize is those equations. What is the application of those equations? Well, the application is extremely simple. If you know here what is the current, the per unit current here, you can, and you know what is the time multiplier setting, you can get the operating time. In other words, if you know the horizontal axis here, you can get the vertical axis. And that is extremely helpful when you are making coordination, okay? Today's softwares, they can make those calculations for you, but in your case, if you want to do it by hand and using your classic calculator, those are the equations for the European standard IC 60255, and this is the equivalent for the American standards, okay? What I am presenting here is the some American information, okay? ABB and Westinghouse, they were involved on the electromechanical protections that they define the CO generation, okay? For many, many years, Westinghouse and ABB, before the standardization, they create those relays. And the CO 6, 7, 8, 9, and 10, They are equivalent but not similar to the ANSI standards. Okay, General Electric, on the other hand, they create inverse and very inverse and extremely inverse relays, but they use a different denomination, a different code. They call it IAC 51, 53, and 77. Okay. Here, if you are interested or you are using CO2 denomination for ABB and Westinghouse relays, you can find the full equation. Okay, what is the reason that I presented this? Because electromechanical protections are still in the market and you are still using those protections, and those equations and those parameters will be helpful for you. Okay. Well, closing this explanation, what I need that you understand is that there are mainly two settings that we need to do when we are working with inverse time delay relays. Okay, non-directional overcurrent relays with inverse time characteristic. Okay, what I need that you understand is that we need to set up the pickup, and that means that the current when the device moves work. Okay, on the other hand, the second setting that we need to take in account is the time delay setting. American or Europe standards, they have different names, but it's the same, and represent the characteristic that create a family of curves that you can use for setting time delays between the curve and for making the coordination work. Okay. Okay. Right now I will go for one example, and this is the example number 1 for the time delay overcurrent relay. Okay. Okay, it's time to put in practice the understanding and the knowledge that we got before. Okay. And this is a first example regarding settings and understanding the curve of the overcurrent relay, the time delay relay. Okay, here we have a very simple exercise. Let us consider a time delay overcurrent relay, and in this case the characteristic that is defining the operation of this device is a IEEE moderately inverse curve. Okay. On the right hand side, you have here the plots, and you can identify the family of the time. This is the family of the time current curve. Okay. They are created for different time delays. Okay, it's time dials. What I want to say is, in the horizontal axis you have here the current per unit values, and here on the right hand side you can have the time dial. Okay, now determine the operating time for a relay that the pickup current is 4.0. Okay, the time dial setting is 1.0, and the current, the operating current is 12 amps. Okay, what I'm trying to explain in this case is we have a relay, there are some settings. The settings is the pickup current is 4. The time dial is number 1, and the current that is coming from the current transformer is 12 amps. Okay. What we need to do is something very simple. Okay. What we need to do is, we know that the current transformer is providing some currents, 12 amps, and what we need to do is convert that current into per unit. And that is the current that we will use here in the horizontal axis, on the horizontal axis. Okay, it's very simple. The current will be the secondary current from the transformer is 12. The setting or the pickup current is 4. 12 divided by 4 represents 3 per units. Okay. I believe all of you realize that the time dial is 1.0. and that means that we are using, there are a family of curve here from 1 to 10, but I only care about this one that I am pointing on the screen, because that it represents the one for the dial 1, okay? And here is very simple. We have here the time dial number 1, yes. We go with the 3 per unit, intercept with the current time characteristic, and go to the vertical axis, and the operating time is 0.34, okay, seconds. Again, what you need to understand is the time dial define which curve here inside the family you will be using. Then the pickup current define the per unit current that you need to use, okay, and the interception represent the operating time, okay. Now let's do this another example. Here right now we have a moderate inverse, IEEE moderate inverse time current characteristic, and now the question is determine the time delay dial settings to reach a maximum operating time of 1 second when the relay setting is a pickup current of 10 amps, okay? And the operating current is 50 amps, okay? Now on the right hand side we have the characteristic with time dials from 1 to 10 for the IEEE moderate inverse, okay? Now the first step is something similar to the previous example. What we need to do is convert the operating current 50 amps, and we know that the pickup current is 10 amps. Converting into per unit, that means that the current is 5.0 per unit, okay? And that current is here 5 per unit, okay? Now the interesting thing here is that we want, if you remember, we want an operating time of 1 second. We plot here an horizontal axis, a line that is horizontal, and that represents the line for 1 second. Then what we realize is our per unit current is intercepting the horizontal line for operation in 1 second at this point here, and that is the time dial number 4, okay? I believe you can see now we are using current, we are using one operating time that we want to know, and we get here the time dial, okay? Solution, time dial number 4, okay? Let's go for example number 3. Example number 3, right now we are using an American relay, a very old electromechanical relay, a CO8. And in this case, the tap setting is, or pickup current is 6 amp. The time dial setting is 1. And we are using, very interesting, we are using a current transformer that is 100 to 5, okay? Now we have here the currents 5 amps, 8 amps, and 50 amps, okay? We have 3 different currents over there, 5 amps, 8 amps, and 50 amps. Now the question is, what is the relay operating time? And it's extremely simple, to be honest. What we need to know is for the first condition, 5 amps. In this case, the pickup current is 6. That means in per unit, that value is 0.83, okay? Now, you must realize there are 2 ways to see this condition, okay? The first thing that you can see is a time of 0.83 is impossible to find in this time current. And because it's impossible to find, that means that that relay cannot work, or that means will never operate for that current, and that is a block. I mean, the relay will not trip. However, if you are not sure, because probably you are a bit confused, what you need to do is the following. We know that for a relay CO8, this is the time current characteristic. What we need to do is extremely simple. We put here the current 0.83 and the time dial that is 1. And when you calculate the time, surprise, minus 18.95. Don't be shocked. That negative time, that is just telling you that that is a non-operational point. I mean, the relay will never operate at that very small current as we are expecting, because it's below the pickup current, and this relay is blocked. Okay? Okay, now let's go to the current 8 amps. The current for 8 amps is transformed into per unit, dividing by the pickup current 6 amps. We get here 1.33. We go to the figure if you want, and you go to the figure and intercept with the curve for the dial number 1, and you will get something like 7 something. Using the equation, you can get the proper number with all the decimal places, and using the equation you will get 7.68 seconds. Okay. Finally, we want to know right now if the operating current is 50 amps. We divide by the pickup current, we obtain 2.5. 2.5 is located here in the on the characteristic. We intercept with the curve for the time dial 1, and we go to the vertical and we obtain the operating time. In this case, the operating time is 1.27. Again, I have used the equation that I provide to you here, the equation for the CO2 relay using the time delay and using the per unit current. Okay. I hope this example allow you to understand the settings. I mean, the pickup current, how we use the pickup current, and also the time delay. Okay. Now I need to run an explanation about something very important for overcurrent protection. Okay, and that represents the principle for grading. Okay. When we are setting protections, overcurrent protection, or any protection, to be honest, what we need to identify is the settings. But identify the settings means that for one specific variable, what is the limit that defines the fault condition? I mean, from this value above, that it will be a trip in the circuit breaker, because that is a fault condition. And below that value, that means that we are in a normal condition, that is a block. Okay. We are working today with overcurrent protection. As a consequence, the variable that we use to discriminate what is a fault or not is the current. Okay. But when we are grading overcurrent protections, there are two different ways to discriminate. Basically, if we are, well, two basic forms to discriminate if we are working in a fault condition or a normal condition. Okay. To be honest, we can summary here. We can use time to create discrimination between fault and no fault conditions, and also the location of them. And also we can use current. It's typical and intuitive that we use the current to discriminate fault conditions and the location of that fault. But sometimes it's very complex. What, to be honest, is that the common practice is that we need to create the correct discrimination, and it's possible to combine time and current together, okay? Probably for you at this stage is not clear what is discrimination using time, or discrimination using current, or discrimination using the combination. But in the next slide, I will try to introduce the concept, okay? Here, I will start with discrimination by time because it's probably the most simple to understand, okay? In this case, in this kind of discrimination, we use time to define the sequence of components, the sequence of circuit breaker operation, depending on the location. Okay, let me start with some very basic and intuitive concept. Okay, here we have, let's say this is a radial configuration. We have a single power source. We have downstairs here, downstream, we have some loads, and this is a radial configuration, okay? That means if we have a short circuit here near to bus bar B, we have a circuit breaker in this position between C and B, one circuit breaker nearby to D, and one circuit breaker between E and D, okay? The logic say if you have a fault near to B, the circuit breaker that is immediately upstream to the fault must be the first one. And then the next circuit breaker to operate must be the next ones upstream. And if anything goes wrong, then we can say that the next circuit breaker to open is between E and D. Well, how do we solve this problem? Well, very simple. The nearest circuit breaker will operate to the minimum time, and that is the case of this circuit breaker between B and C, and the operating time will be T3. Then there is operating time T2, and T2 will be bigger than T3, and that is the operating time of this circuit breaker near to the bus bar D. And finally, we define an operating time. The longest one is for the circuit breaker between E and F, okay? Something that you must realize is the fault is located near to B, but when you are moving near to the source, if you are using purely time discrimination, the problem is that you need to use first definite time delays over current relays. You need to use definite time relays. Okay, that is the first thing, and they are not quite friendly with other devices like the fuses, for instance. I know protection people, they can complain about my explanation because they will say that definite time relays, they are not quite useful and not quite typical, but what I want to do is explain time discrimination to my students, okay? In this case, time discrimination means that the operating time of the relays will increase when you are far away from the fault, okay? In this case, that is a possible solution. However, there is a interesting thing, okay? The faster circuit breaker, the faster operating time will be near to the fault, and the big operating time will be far away from the fault, okay? That creates a problem. Because if you remember short circuit analysis, when you are far away from the generation sides, the short circuit currents are lower, and when you approach to the generation side, the short circuit currents start to increase. And that is not what we want. I mean, we don't want that a fault takes so much time to be clear when you are near to the generation side. There is a reason that discrimination by time alone is not typically a unique solution, okay? Then when we have another method, and that is discrimination by current. To be honest, for many years we have been using discrimination by current, especially a distribution system. And one of the reasons is the physical reason that if you are far away from the generation point, the short circuit levels are smaller. But when you are start to moving nearby to the generation, the fault currents start to increase. To be honest, that as a first glance allow you to create a very simple and very basic rule for discriminating faults. However, I will show you some of the complexities relating with this discrimination by current in the next slides, okay? Again, when you are using discrimination by current, you use the short circuit levels as the main indicator to define the fault condition. But the problem is that when you are moving inside the power system, short circuit levels are changing. And it's not only, and that is the key word, and it's not only when you are moving inside the power system. There are many other conditions that they can modify the short circuit levels, okay? Okay, imagine that we have this small power system over here on the right hand side. There is a generator, there are coupled cables, there is a step down transformer going to some distribution feeders, okay? In this example, the idea is to show you that they are fault levels, okay? Fault levels, F1, F2, F3, F4, okay? What I will do at the very beginning is, okay, let's calculate. Let's put some numbers about the short circuit current at the location F1, okay? F1 is the location at the very end of the cable 1, okay? It's very simple. We divide the voltage by the equivalent impedance using Ohm's law, and that will be the impedance coming from the external grid plus the impedance coming from the cable, okay? It's very simple to see that we are using an external source, and in this case the levels is 250 MVA, and the source is also 11 kV, okay? For that reason, we can estimate the source impedance, 0.484. We know the data for the cable, 0.24 ohms. We put the number together, and what is the surprise here? They are not surprised. The fault levels at F1 is 8.8 kiloamps, okay? That means that if we put here a relay, overcurrent relay, that overcurrent relay must have a setting that should be 8.8 kiloamps, okay? Because a fault here represents that we have a fault in this cable, and as consequence, this circuit breaker must open, okay? However, what's happened if we think about a fault at the location F2? Well, the location F2 is a very small location. This is the end of the cable. We have a bus bar, we have a circuit breaker. To be honest, the impedance between this point, bus bar B, and the other side of the circuit breaker must be almost zero. But let's say that is not zero, it's something very small. To be honest, the short circuit here and short circuit at point F2 and short circuit at point F1, they are almost the same value. As a consequence, it's not practical. One thing that you must realize right now is that it's not practical. It's not practical to distinguish faults located at F1 or F2 using currents, because if the impedance between the points F1 and F2 is extremely small, the changes on the short circuit currents will be almost zero, and differentiating between F1 and F2 will be a massive problem for the overcurrent relay based on currents, okay? However, I want to show you another. This is one case that discriminating faults using currents start to be a problem. What can be a solution? Well, that the circuit breaker located here use a directional overcurrent relay. Okay, the fault level here is the same fault level here, but if the fault is located here, the direction is going to the right, but if the fault is of F1, the current is going to the left. As a consequence, you can say 100-degree angle, and the directional protection will be able to identify. Okay, this is just to give you a comment that that is related with the solution. Okay, I know some of my colleagues from the protection area, they will say, okay, a bus bar, a short circuit near to the bus bar, you have another protection scheme for bus bar and so on. Yes, I know, but we are in basic now. We are trying to introduce basic concepts related with discrimination by current to my students, okay? Okay, I say a few slides ago that it's classical that the short circuit level change, okay? One very specific situation is depending of the location, okay? That is the quite typical. If you are working in a radial system and you move from the tail of this feeder to the head of that feeder, I mean, going close to the generation, the short circuit levels increase. And that is very simple because when you are at the tail of the feeder, you have a big Thevenin equivalent impedance, short circuit levels low. When you move near to the generation side, the Thevenin impedance decrease and you have a high short circuit levels, okay? I am talking about three-phase short circuit levels, okay? But I say to you that there are some other cases where the short circuit levels, they change, okay? And something that you must realize is depending of the operating conditions, the short circuit level can change. For instance, if you are working, if the system is operating and the load is low, you have less generators operating inside the power system, and as consequence, the total Thevenin equivalent impedance is higher and short circuit lows. But if you are at the peak level and you have a very high load, there are more synchronous generators connected to the grid. There are more machines in parallel, and the total equivalent impedance is decreased, creating big short circuit levels. At substation, at transmission, distribution level, sometimes you have 2 or 3 transformers working in parallel. When the load is low, you have only 2 transformers, but if the load increases, you can have 3 transformers in parallel, decreasing the impedance, increasing the short circuits. In this case, I would like to show you another limitation about discrimination by currents, okay? In this case, we have the same radial system, but right now, let's modify the short circuit levels at the source, okay? Right now, we are moving from 250 MVA short circuit level to 150 MVA short circuit levels, okay? Three-phase short circuit level. In this case, this is the equivalent impedance. This is a reactance for the supply or generation impedance, and we know the impedance of the transmission line, and we can get here right now the fault levels at F1 is around 5.4 kiloamps, okay? If you remember, when we are using high generation, 8.8, but when you go to minimum generation, you are reaching levels of 5.4, okay? That means we have a huge decrease on the short circuit levels. Even if you put the fault here at the generation bus bar at C, the maximum short circuit level available is 6.8 kiloamps. That means if we set up the relay for 8.8 and a fault happen, to be honest, this short circuit will stay forever over there because the settings is 8.8 and the available short circuit current when you have low generation, when you have low short circuit capacity, is 5.4. Okay, again here there is a problem because there is no way to discriminate the current if we use the setting using 8.8 kiloamps. Okay, finally what I want to do here is, okay, let's go back again to the scenario of maximum generation, and now let's calculate the short circuit. Let's calculate the short circuit and the short circuit levels at the end or the tail of this circuit. Okay, at the end or the tail of the short circuit is positioned here, F4. Okay, position S4, again using basic Thevenin, is the voltage divided by the total series impedance. In this case we are using maximum generation. We have a transformer in the middle that is 7% impedance, and that transformer, the problem is that it's introducing a big impedance. Okay, if you compare, the source is 0.4, the cable is 0.2, the second cable is 0.04, and this transformer is including a huge reactance here, 2.11. Okay, as you can see, the short circuits, they are reduced to 2.2 kiloamps. Okay, in this case, if we are interested on the circuit breaker near here to B, the circuit breaker B, and the fault is located at F4, well, we have a problem because that circuit breaker with that very small current will not operate. If we assume 20 or 30% of the error on the relays, and also if we include variations on the impedance, that means that the settings of the relays must change and must adapt when we are using different levels, short circuit levels inside your system. Okay, now finally, just for a short comparison, now let me talk about a fault at F3. Okay, F3 is the point that is on the high voltage side of the 4 MVA transformer. Okay, F3. F3, if we calculate the short circuit levels, if you look over here using the maximum generation capacity, 250 AVA, the short circuit current is 0.3. But if we are using the low generation scenario, or the low fault levels of the power plant, 130 MVA, the current it will be 5.2 kiloamps. Okay, there is a big gap between the high short circuit level and the low short circuit levels. As a consequence, again, talking about the circuit breaker that is located near to the bus bar B, the relay B, in theory, this will be able to correctly identify faults anywhere inside the 11 kV cable feeding to the transformer. However, if we go downstairs to the position F4, it will be a problem for this circuit breaker to discriminate the fault. Okay. That is the reason that I identified there are some weak points on the overcurrent protection settings based only on currents. And that is the reason that protection engineers, they start to think about combining two different grading criteria, using discrimination, time, and current at the same time. Okay. What is the idea of using combined time and currents? Okay, time grading, time discrimination has some advantages and some disadvantages. current discrimination, it has some advantages and disadvantages. What if we take the best of each discrimination and we combine together? Okay, what is typically is that we don't use one of the discriminations sometimes alone. We can use discrimination by time alone, but the problem is that the most dangerous faults will be clear in a very long time. And if we use discrimination by current, we have the great problem that when the impedance change in the system, the short circuit level change, and also if the impedance that is separating 2 points is too small, the discrimination will be a problem. What if we start to play with the curve and we start to make settings that we can modify time and current? Well, to be honest, the disadvantages of time and current discrimination can be overcome if we start to move the time current characteristic. On the right hand side, you can see two relays, relay B and relay C, and you can see the operating time of both of them. As you can see, if we start to play with the times and currents, when you are playing with the times and current, you are moving to the left or to the right, and when you are playing with the time, you are moving to the top or down, okay? And that is when you start to use different settings, current time settings for relays depending on location for lengths. Now, what is the problem? The problem is that you must have a very good model of your power system. Then you need to identify clearly the scenarios that allow you to get maximum, minimum short circuit levels. And also you must understand the configuration of your system to identify what is the longest time that you must trip a circuit breaker, okay? And that is when the situation starts to be difficult. Because what I was talking about, selecting times, selecting currents, and coordinating the distances in time and currents between the different overcurrent relays, that is what we call coordination procedure. Okay, the coordination procedure is to define the proper settings of the non-directional overcurrent relays. Okay, that means settings for currents and settings for time. Okay, but the first thing that you need to do is you need to understand and have a full picture about the fault short circuit currents in your system. Okay, you must know what is the current that is flowing in any part of your system. Okay, if the power system is large, well, it's a problem. Okay, it's a problem, because identifying what is the condition that will define the short circuit levels, that is a very important problem. However, today we are using softwares. We are using software like the Excellent Power Factory that allow automation, and now calculating and getting the fault levels for the most critical conditions and any other scenario is extremely simple. Okay, well, coordination procedure, what you need to do is first you need to collect data. Okay, you need to collect the data, especially if you are evaluating relay settings. Single line diagrams of your system, including the impedance. It can be in real unit ohms, it can be in percentage, it can be in per unit, but you need a full representation of your system. Then you need to know the maximum and minimum short circuit levels, okay? And also, because you don't want your system, your protection system, your overcurrent protection system tripping in load conditions, you must be aware what is the maximum low current in your system, okay? Because the maximum low current at your protection device should be a no trigger, okay? You will never want a overcurrent, non-directional overcurrent protection tripping for low currents, okay? Then you need to have a proper understanding about some natural overcurrents that can happen inside your power system, okay? let me say again, you need to have a proper understanding about the natural overcurrents inside your power system. What does mean natural overcurrents? Natural overcurrents are overcurrents that happen in normal operating conditions. For instance, when you are switching on, when you are starting up an induction motor, there are a peak, there is a maximum current that you will have in your induction motor. You must know those values, okay? Because your overcurrent protection must not trip in that case. But there are many other characteristics. For instance, the inrush current of transformers. When you are energizing a transformer, there is another big current with a very short direction. You don't want the overcurrent protection tripping for that, because again, it's a normal overcurrent in your system. Okay. Also, it's quite important that you must understand that every single component inside the power system during a fault condition, the short circuit current is moving through. A transformer, if you have a fault on the low voltage side, there are current moving inside the transformer and affecting the life of your transformer. For that reason, there are something that we call the decrement, the thermal withstand or the damage characteristic of transformer, cables, and motors, okay? We need to have a proper understanding about those damage characteristics, okay? And then you will start with the full coordination. Relay settings, you need to start with the shortest operation time at the maximum fault levels. And then you will start to plot the curve of all the relays and all the protection devices, okay? It's typically that we use something that we call the plot time current, okay? In that plot time current, as I present before, we need to start to present all the devices, all the relay characteristics, fuses, reclosers, and so on, okay? And it's expected that you will do this at the lowest voltage base, okay? That is the most predominant voltage in your system. Another ways is that you present everything in AVA in base in per unit, okay? Okay, something that I will say here, something that I will say here, and probably my protection guys, they will not agree with me. Basic rule for overcurrent protection relay, okay? They are not basic rules. When you have many years doing overcurrent protections, you will realize that every single case, it's different. It's amazing. Every single case is different. It's like a human being. However, there are some common aspects. There are some basics that you can say, okay, that is some best practice. I will not say basic rules. They are not rules. There are some just advices that we can give you in order that you can have a relative good starting with the non-directional overcurrent protection, okay? One of them is try to use relays with the same operating characteristic. I mean, if you are using inverse time, try to put in the same series configuration relays with the same characteristic. Is that possible? Well, my friends from the utilities and from the power protection side, they will say, no, you are crazy. In real life, we have so many protections, we have so many manufacturers that in real life that is not happening. Okay. But that is something that if you can do it, that will save your life. But in real life, it's not necessarily true. Okay. Then what we want to do is start from the fastest, the relay that is located far away from the source, and have the settings equals or similar or less than the relay behind it. Okay. That means that you will start to go from the tail of your feeder to the front of your feeder, okay? And the settings will be increasing in the time that you are moving to the source, okay? Again, my protection guys, they will say, no, this is not a good practice. Well, if you are working in distribution feeders and you are using just, you are calculating only phase protections, I mean protections against three-phase short circuits, that is a rule that, it's not a rule, it's a practice that could be useful, and probably 99.9 times it will be working, okay? Okay. Now, what I will do is right now, when I was creating this teaching material, I was thinking, okay, I will present some methodology in order that my students will be able to use this like a cookbook and set the protections, and then I say, no, you cannot do this, okay? You need to keep the mind of your students open, and they must realize that every single case is a situation that you need to use your brain, your capacity of reflecting and thinking about what is going on, okay? For that reason, I didn't call this a methodology. The next sections in this presentation I call application, because I would like to show you with a generic example what is the situation? What is the situation? How do we set up relays, overcurrent relays, non-directional overcurrent relays? How we can set, how you set up those settings? Okay, I will start with, again, a protection that some of my colleagues in the field, they will say, no, that protection is not quite used, sometimes can be used, sometimes not. But for the academic point of view, from people that they are just starting to understand protection coordination using a non-directional overcurrent relay, that will help, okay? Let's start with a very basic case, okay? We have a source, we have two cables over there belonging to a same feeder. We have a line that is moving between A and B. We have a line that is moving between B and C, okay? We have a source. We have two sets of transmission lines, okay? And they are definite time overcurrent relays installed here are A, and here are B, okay? They are transformer current here for the circuit breaker. They are current transformer here for the net circuit breaker, okay? They are loads. They are loads here at A, B, and C, okay? Okay, what is the problem here? The typical problem here is, okay, imagine that you know all the loads and fault currents, okay? You know all the load, the current conditions, loads and fault. Now, how do we set those relays at bus bar A and B so that in this feeder we can get overcurrent protection, non-directional overcurrent protection as a primary and backup protection, okay? Let me say again, we know all the current levels. We know the load level and we know the short circuit levels, okay? And we have definite time relays located here, A and B. What should be the settings in order that this feeder is completely secure and protected, and considering primary and backup protection, okay? Something that you must realize is that the relay B here is protecting the section B and C. That means that this relay here, B, is the primary protection for this section, B and C. A fault at this location, the primary circuit breaker that must open is CBB, and it's because RB, the relay, is the primary protection for this section. However, relay A is a bit more complicated, because relay B, the problem is that this relay must be the primary protection for the section A and B. I mean, any short circuit inside A and B, the relay RA must open, okay? But also, if a fault happened in the section BC and the relay B doesn't open, that means that the relay A must be able to provide backup protection for faults located between B and C. Okay? That is what is the basic explanation here. We have primary protection for line BC provided by the relay B, and we have primary protection for the line AB and backup protection for BC provided by relay A. Okay? Okay. Now, what you need to understand is when we are inside power systems, we have a set of different currents, okay? I will go for the basic for the understanding of my students regarding overcurrent protections, okay? There are many other things that I can include here. I will not go there, okay? My protections guys, they can put comment below and say many things, but I will focus on load currents and fault currents, okay? Load currents, we have the normal load current, and that is the current that is typically consumed by the or demanded by the load, and there is a maximum load current, okay? What I'm trying to say is that the current, load current, have a limit. From there to the top, it's not allowed, okay? Okay. Second, when we have short circuit, you must remember my explanation before. Depending on the operating conditions, we can have maximum short circuit levels and minimum short circuit levels, okay? Now, what are the two conditions for the pickup settings of these relays, okay? Well, very simple. We don't want the relay tripping with currents below the maximum load current. No, we don't want that, okay? Because that means that it will trip the circuit breaker during low conditions. But we don't want the circuit breaker tripping only a maximum short circuit level, because if a low level of short circuit happen, that means that the circuit breaker will not see the fault, okay? Well, what you need to understand is that the region that the circuit breaker must operate, the area for the pickup current, is between the maximum current, maximum load current, and the minimum short circuit levels. Because anything above the minimum short circuit level is a fault, and we are in problems, okay? Here we have condition 1, the pickup current must be above the maximum current. Condition 2, the pickup current should be below the minimum short circuit levels. And we have an equation for the settings of the pickup current, okay? Again, we are working with a definite time overcurrent relay, okay? Okay, however, there is something extremely important, okay? If we are working with this relay here and we are using the relay as a primary protection, okay, we need to define the setting of this relay based on a current that is above the maximum load and below the minimum short circuit current. But if we are working with the next relay, relay A, that is upstream of the relay A, there are some considerations that we need to take in account. There are considerations regarding primary and backup protection, okay? Okay, let's see the following. If you look over here, what we can have at the very beginning is the moment that the fault is inserted inside the power system. At that moment, the overcurrent starts to happen, and the first relay that will notice, both of them will notice the short circuit, okay? But one of them must take action first, and that is the relay B. The relay B must take action because it's the primary protection, okay? As a consequence, after the operating time, this circuit breaker must operate and send the signal to the circuit breaker to open, and the circuit breaker will take some time to open, okay? What I'm trying to say is from here, from the fault instant to this location, that is the process of stopping the fault currents inside the line B and C, okay? Okay. But what's happened if we want the protection A to be a backup protection for the fault between the section B and C? Well, that this relay must wait until the first relay operates, send the signal, and stop the short circuit current between B and C. But if there is not a successful operation of the circuit breaker B, then the relay must trip, okay? That means that the relay B must wait until this time, waiting that the circuit breaker B and the relay B make the work properly, and if not, then the circuit breaker A must trip as backup protection of the line BC, okay? Probably this is a bit confusing for my students, but I will try to show you very simple, okay? What I try to show you is, okay, we are using definite time relays. That means the relay B has a time setting that can be adjusted. In this case, we select the minimum. Why do we select the minimum? Because we don't have any other relay downstairs of the relay B. And as a consequence, we don't need coordination downstream of the relay B. For that reason, we set the relay to the minimum setting, in this case, 0.1 second, okay? However, that is the primary protection. What I'm trying to say is that the relay B, it will send the signal in 0.1 second to the breaker in order to stop the short circuit current. However, what is the problem? If the relay A is offering backup protection to the relay A must be slower and must wait time until the relay B and the circuit breaker B, they do the job, okay? What I'm trying to say is the following. The time that the relay A must wait is what we call the operating time of the relay B, plus the time of the operation of the circuit breakers. And in this case, we are assuming that the circuit breaker B use 0.5 seconds to clear the fault. And then we add an overshooting time, and that overshooting time is the time that we get for safety, for waiting that the circuit breaker and the relay make the job, okay? In this case, for the relay A, it will be 0.1 coming from the operation of the relay, 0.2 that is coming from the operation of the circuit breaker, interrupting the current and extinguishing the arc, and then 0.2 seconds, that is the overshoot time. Finally, the time used for the relay A to operate, it will be 0.8 seconds. Okay? Extremely simple. Some books use this interval like selective time interval. Okay? The 0.2 seconds is used to create differentiation in operation between one and the other relay. Okay? Okay. Here I want to show you what is the selection process that you need to use. And for the relay B is extremely simple. Time setting, we use the minimum setting, that is 0.1 seconds, because there is not another relay below. Okay? Because if we have another relay downstream or down stairs of this relay, we need to consider all the times, okay? Circuit breaker time and overshoot time. Pickup current. The pickup current is extremely simple. The pickup current must be above the maximum load current and below the minimum short circuit levels, okay? In this case, the relay B will be providing only primary protection on the section BC. Then we have the relay A. The relay A has two functions. First, primary protections, and then secondary protection, okay? The pickup setting, let's start with the simple one. The pickup settings is extremely simple because the primary protection will be defined by the current. In this case, we will use a current that is below the short circuit levels and higher than the maximum load level, okay? And then we have the very interesting time that we need to wait, okay? For a fault between A and B, the primary setting will be the current and it will trip the. But if the relay B plus the circuit breaker doesn't open, we will wait some time and then we will trip the relay A. That is extremely simple, okay? It's basically logic, okay? Okay, next case. The next case is, now let's work with time delay relays, okay? Non-directional overcurrent relays, okay? What I will do now is I will use the inverse definite minimum time relays for protection in a distribution feeder, okay? In this case, the situation is similar to the one that I presented before. We have a radial feeder. We have two sections, A and B and C. There is a relay here that is providing primary protection for this region, but also backup protection for the next one. And the relay B is providing protection for the section BC, okay? We want those relays, relay B providing just primary protection, and because they are not more protection downstream of relay B, and relay A, it's providing protection to the relay downstairs, that is the relay A, okay? Okay, now the question is, how do we set up those relays in order to provide, primary and backup selection? Okay, now what we want to do is select the settings of the inverse time relays overcurrent and non-directional overcurrent relays installed in the feeder. Okay. The first step should be, I didn't tell you in the previous example, but it's typical that you need to define the current transformers. Okay, when you are creating or defining protection from the very beginning, I mean a system that will be installed, you need to define the CT ratios. Okay. In this case, you need to define the CT ratios. That is the step number 1, and then you will need to define the current settings. Okay. Something that is very interesting that you must know is that sometimes you know only the load current and you don't know the maximum load current. That is the case in some distribution systems. And what is the best option? What is the solution? Well, some cases there are some people that they say that you can assume 25% overload. Okay, you can define that percentage, 25 overload. I don't know that people from the industry will say no, you are crazy. There is not a specific paper saying that, but it's a practice that can be done. I mean, that defined not the overcurrent protection. Okay, I would like to clarify here. It's not defining the overload protection. It's defining the starting point of your overcurrent protection. Okay. Another thing that my student must be aware is that the CT, the current transformers, they are standardized. Okay. For selecting the current transformer and for specifying the current transformer, I highly suggest that you go back and watch my class about CT and VT. Okay. Now what we are here is because settings relays for settings the parameters, settings the related to relays. Okay. In this case, the relay B. It's very simple and straightforward. Okay, the pickup current of the relay B, it's very simple. Is feeding the load C, and we consider some overloads. That means that the pickup current must be at least above the maximum current. Okay, and also the pickup current must be below the minimum short circuit current. Okay. Because relay B is the last relay in this feeder. There are not more protections down the stream, and as consequence we can say, okay, let's select the fastest operation for this relay. In this case, we will say let's use 0.1 seconds. Okay, it's typical that we select the smallest time setting for the relay when they are located at the tail of the feeder. Okay. Now, where the situation starts to be quite interesting is the situation regarding the settings for relay A, because relay A provide primary protection for the line BC, but at the same time provide backup protection for relay B. If there is the setting for current is extremely simple. The pickup current will be evaluated between the maximum current that is moving across this relay, and that is the current from the load B and C and the overload that we consider, and then the short circuit at load C. Okay, back boost bar C. Where is interesting is that we are offering the backup protection on relay B and relay A by using a time separation. Okay. That means that the time setting will be the operating time of the relay B plus the operating time of the circuit breaker, that you must know that because the manufacturer, plus some overshoot time. Okay. Okay. It's time for the last example of this session. Probably the most complex but the most complete example, and In this case, we are interested on making on defining the settings of the non-directional overcurrent relays using IDMT relays at a distribution feeder. Okay, this is the classical topology that we have been using now because it's the classical topology for applications of non-directional overcurrent relays. And here what we want to do is, again, there are two sections, A, B, and B and C. There are two relays, relay A and relay B. And those relays, they are, as I say to you, IDMT, okay, overcurrent, non-directional overcurrent relays. In this case, we know loads. We know loads A, 200 amps, load B, 160, load C, 80, okay? That means that this is the load current. We don't have any idea about the maximum load current, okay? That means we need to make some assumptions. We will do that later. But what we know for sure, and what we are totally clear, is that short circuit levels, minimum and maximums, are provided at bus bar A, B, and C, okay? Well, what is the first step? Well, the first step, as I said before, this is the most complete example that you can see. The first step, let's say, start defining the CT ratios, okay? Imagine that this is a feeder that you are working because it's at planning stages, and you are interested on creating this feeder and installing the protections, okay? In this case, we need to define the CT ratios. Again, it's typical that for overcurrent protections, we start from the tail of the feeder and then we move to the head. For that reason, we will start with the relay B, okay? Relay B, the relay B, if you look the current transformer, CTB, the CTB is taking measurement from the current that is going to the load C. That means that the current that's supposed to be here is around 80 amps, okay? However, we don't specify the transformer current using the nominal current. We assume some overloading, and in this case, we are assuming that they are 25% overload, okay? I know that people will come back to me and say, and put comments below, that is not a normal practice. Okay, it's not a normal practice, but is useful at this moment, and it's valid for many applications, okay? 25% overload is a decent margin, okay? For that reason, when we put the number together, that means that the current that is going, for the primary of the CTB is 100 amps, okay? We are assuming that the secondary of this transformer is the classical 1 amp current that is going to the relay, okay? For that reason, it's extremely simple. We are using here a current transformer that is 100 to 1, okay? Simple. Now what we need to do is, okay, if we are using 100 amps to 1, the relay B, okay, we can use a plug setting. The 1 amps, okay, 1 amps. Okay, then relay A. Relay A, as you can see over here, the current that is moving on this line, through this line, AB, the current should be 160 plus the current on load C, 160 plus 80, that should be around 240, but we are allowing 25% overload. That means that the maximum current moving on the line AB, and that is the current that should be moving across the the CTA is 300 amps, okay? For that reason, we will select the primary using 300 amps, and then the secondary, we assume that we are using relays, that they use 1 amps. For that reason, we specify the current transformer again. The current transformer at position A will be 300 to 1, okay? In this example, it's very academic example. In this case, both current transformers, they are matching standardized values for currents, okay? If your calculations give you a number that is not matching a standardized value, you must go and use the immediately above level of the standardized, okay? Okay, now again we are using 1 amp, so we will define the clock setting for the relay A. In this case, we will define the setting for the relay A as 1 amps, okay? Okay. Now is the configuration of the time settings, probably the most important settings. In this case, we are selecting the time setting for the relay B. The relay B is located at, let's say, near to the tail of this feeder. There are no more relays down the stream. As a consequence, we can say that the time setting of this relay will be the fastest. In this case, we can assume that the relay will be working at 0.1 seconds. Okay, that is the setting for that. But where the situation starts to be quite interesting is regarding relay A. Because relay A, the situation is that relay A is providing primary relay A is providing primary protection for the line A and B, but is also providing backup protection of relay B. For that reason, we need to take in account that the time setting for relay A must be defined considering the operating time of relay B plus the time of the circuit breaker to open and interrupt the arc plus overshooting time, okay? Now the sensible part is selecting what is the time setting for relay A in order to provide backup to relay B, okay? Now probably what we need to do, for sure what we need to do is we need to define what is the operating time of relay B, okay? That is a critical point here in this solution, okay? And to do that, what we will do is the following. We know that we are using a relay that is defined by IDMT curve, and in this case we are using a relay which the operating time is defined by this equation over here, okay? What I'm trying to say is this equation over here define the operating time of both relays. Both relays have the same operating, both of them, they have the same operating characteristic, okay? Because both of them have the same operating characteristic, is simple for us, it's extremely simple for us to obtain what is the operating time, to obtain the operating time for the relay B, okay? And that is the next step. The next step that we need to do is we know that the maximum short circuit levels, we know that the maximum short circuit level at the bus bar B is 3 kiloamps, okay? Because we define a current transformer that is 100 to 1, we can obtain what is the current referred to the secondary of the CTB. Using the transformer ratio 100 to 1, the fault current at B, 3 kiloamps, is transformed into 30 amps at the secondary of the CTB. From there, because you must remember that we are using a pickup current of 1 amps, we can obtain the current in per unit, okay? And that is what we need, because in this case, you must remember that we are using here the current in per unit, and we are using here the time setting that we already defined, 0.1 seconds, okay? It's extremely simple. Now what we need to do is settings, current settings, 0.1 seconds, and using the per unit current 30 amps, we obtain from the curve that the operating time of this relay is 0.1988, we can say is 0.2 seconds, okay? That is the time that this relay will send the signal to the breaker to open when there is a current of 3000 amps on the primary of the CTB, okay? Okay. Now let's assume that we are using a breaker, and this breaker is a very slow breaker. Let's say that is 0.5 second, the time that this relay require to, since when the signal arrives from the relay, this relay take 0.5 second to open the contacts, stop the current, and extinguish the arc, okay? This is the operating time of the circuit breaker, okay? Then we need that the relay A provide backup to the relay B. As a consequence, the minimum operating time, as you can see here, the minimum operating time should be 0.2 seconds coming from the relay B plus 0.5 seconds coming from the circuit breaker, and at least 0.7 seconds are needed in order to say, okay, relay B and circuit breaker B must operate. However, for safety, we are adding a 10% overshoot, okay? What I'm trying to say is that right now we are adding 10% overshoot to allow 0.7 seconds delay between the time that the relay B is supposed to operate and the time that the relay A will provide the backup protection, okay? Now coming back, the maximum, the operating time that we need to define the setting for relay A must be 0.2 seconds coming from the operating time of the relay B plus 0.5 seconds coming from the circuit breaker B, and then we are adding 10% in order that the operating time of the relay A must be 0.77 seconds, okay? Now as you can see, the relay A must wait until 0.77 seconds in order to operate, okay? But now the question is, Now our question is, okay, 0.77 seconds, okay? In that case, the full current should be 3.0 kiloamps, but at relay A, we are using a different current transformer that is 300 to 1, okay? As a consequence, when there is a fault on B, and that fault is 3000 amps, at the secondary of this current transformer, the current should be 10 amps. That means 10 amps at the secondary of the current transformer A, okay? Now, that current is converted into per unit because few slides ago we defined the pickup current as 1 amps, and as consequence, we know now that the current should be 10 per unit, okay? Now, what I am doing is trying to define the setting of the time setting of the relay A, okay? Now you can see here again the equation that defines the IDMT relay characteristic, time versus current. And you must remember that this is the operating time, this is the per unit current, and this is the time setting, okay? What I'm trying to say is, in this equation over there, in that equation over there, we know this value because this value is 10 per unit. We know this value because it's the time that we need to wait in order to provide backup protection, 0.77 seconds. And this value over here is the unknown variable, okay? Now what we need to do is just basic mathematics. All of my students are very good in mathematics. And from there we obtain, and this is the value for the time setting. I mean, the time setting must be 0.26, okay? Okay, at this moment we have defined, if you go back to the previous slides, we define the current transformer A, we define the pickup setting of B, we define the current transformer A, we define the pickup setting at the relay A. Then we define, and it was extremely simple, the time setting for relay B. The time setting for relay A was a bit more complicated because we need to wait that the relay B work, and then we add 10% of operating time, and from there, using the equation of the IDMT relay, we can get the time setting, okay? That is quite interesting and simple. What is the next step? The next step is we need to be sure that everything is properly working. And right now, what we will do is let's use the minimum short circuit current at bus bar B. And using the minimum short circuit current at bus bar B, we can use the transformer ratio 100 to 1. And using the current transformer ratio, we obtain that in the secondary we will have 20 amps. The settings for the current pickup of relay B is already defined, 1 amps, and the per unit value at minimum fault current is 20 per unit, okay? What we need to do now is calculate the operating time of the relay B, okay? We can do that extremely simple because we know the equation that defines the operating time of the relay, and we already know what is the time setting of the relay, 0.1 seconds. What is the interesting thing? For minimum short circuit levels, we get an operating time of 0.26 seconds, okay? If we compare with maximum current, okay, if we compare with maximum current, if we are using the maximum current, the operating time is 0.2 seconds. If the currents go to the minimum level of 2000 amps, the operating time of this relay will be 0.226. There is no surprise, we are using an IDMT relay. As a consequence, lower current, longer operating times, okay? But now what we will do is, again, this circuit breaker is quite slow, 0.5 seconds. Using the operating time 0.5 seconds, we can obtain the operating time, the minimum operating time for the relay A. That means that the relay A must wait 0.726 seconds. That is the minimum time to provide the backup protection. And considering 10% of overshoot, that means that the operating time of the relay A, considering minimum fault levels at B, should be around 0.8 seconds, okay? 0.8 seconds, okay? Okay, then what we want to see is what is the actual operating time of the relay A. What is the actual operating time of the relay A? Well, it's very simple. We know that the minimum short circuit current bus bar B is 2000 amps. And using the transformer ratio of CTA, we obtain that the secondary is 6.6 amps. And now what we want to do is, okay, for relay A, the settings for the pickup current is already defined, 1 amps, and then the per unit current will be 6.66. Okay, using the full equation that we know for the IDMT relay, we know that we know the time setting of the relay. We know the time setting of the relay because it was calculated early. We know what is the current in per unit because we already calculated at the minimum fault levels. And now we obtain that the operating time of minimum current is 0.94. Okay. In this case, the idea of calculating the operating time of the relay at the minimum short circuit fault is to assess the selectivity between the relays when we have high short circuit level, maximum short circuit level, and low short circuit levels. I think you can see that the result here is that the operating time of the relay A is 0.94 seconds. this number is larger than the minimum operating time of 0.8 that we calculate here. .8 seconds is basically the time that we need to consider in order that the relay A offer backup protection, and 0.94 is the time, the operating time that the relay must act when there is a minimum fault levels at the bus bar B. As a consequence, as we demonstrate here, 0.95 is greater than the minimum operating time of 0.8. And as a consequence, we keep the selectivity between the relays A and B, okay? Well, what is the next step? The next step is create a summary about the protection settings, and in this case we are presenting the single line diagram, and in this case we show over there, we are showing there that the current transformer at relay B is 100 to 1. The current transformer at relay A is 300 to 1. Then we present the setup, the current setup. There is both relay have a current setup for a pickup current of 1 amps. And then probably the most complicating part, it took more calculation, the time settings for the relay B, 1 second, and the time setting for the relay A, 0.26, okay? However, with all the calculations shown before, we are completely sure that these overcurrent protections are providing primary and backup protection on relay A, and primary protection on relay B, and also with the sensibility running the calculation for minimum currents, we can identify that we are able to provide selectivity between the relays A and the relay B. Okay? Okay. Well, finally, I would like to close this presentation presenting a short summary about what we have done today. Okay, this chapter we present a very basic and very brief introduction about overcurrent protection. Especially it was dedicated to non-directional overcurrent protection with emphasis and examples to protection, overcurrent protection of distribution feeders, okay? At the very beginning, we present a general discussion. About overcurrent protections and the main protection device used at transmission and distribution systems. We present the fuse as the oldest, probably the most used and a low voltage level device, the fuse. We talk about the Recloser and also the Sectionalizer and the overcurrent relays. Okay, then we spoke about the main features of the current time characteristic, especially about the instantaneous and the definite time overcurrent relays, but also inverse time relays, okay? Some elements of the principle of time current discriminations were presented, specifically discrimination by time current and overcurrent. We showed that the discrimination by time alone has some drawbacks. Also, discrimination considering current alone also have some problems, especially when we have impedance, source impedance that is changing. Then a very short and very brief overview about the coordination procedure. And finally, we run a full explanation. I will say that is probably the best explanation about application of overcurrent relays for protections of a distribution feeder, okay? Before I close, I would like to say that there is an example here, a homework some of you can take away. In this case, there are 3 relays. There is a feeder with 3 sections, 0, 1, 1, 2, 1, 3. And over there, you know the load currents. Well, not the load currents, but at least you know the loads. And then you know the short circuit levels, minimum and maximum short circuit levels. And the task here is to do the top settings and the dial settings. In this case, my students, you must take in account that in this case we are using the old electromechanical protections, the CO8. And in this case, the overshoot that we want to use for coordination is 0.3 seconds, okay? Also, additional information, this is an American system, 60 Hertz, and also 34.5 kV, that is a very American primary distribution system voltage level, okay? Finally, you can assume that the values of the load presented here, ABC, they are represent the maximum load. That means that you can use those loads for the settings of your relays, okay? Well, again, it has been extremely pleasure being here and talking to all of you and presenting this short explanation about overcurrent protection, few examples, and I hope that you like this video. Thank you very much for your attention. See you in the next video.